Many different kinds of instruments can be used together as a system to control the process variables that are associated with the production of products. Instrument systems are important because without them, it would be difficult for operators to keep up with every process variable in the plant at the same time. Instrument systems monitor and adjust process variables at key points to keep the plant working safely and efficiently. Instruments are devices used to measure, indicate, or control a process variable, or transmit information about a process variable. An instrument system is a group of instruments and associated devices that work together to continually monitor a process variable. Some systems also control the value of the process variable. For example, this tank is part of a system that supplies water to several process systems in a plant. In order for a continuous supply of water to reach the various systems, the level of water in the tank must remain within a specific range. To make sure that this is achieved, the water level in the tank is monitored and controlled by an instrument system. This instrument system includes a transmitter, which senses the value of the process variable that's being monitored, in this case, the level of the water in the tank. The transmitter sends a signal, which is proportional to the value of the process variable, to other instruments in the system. This instrument system also includes an indicator, which shows the current level of water in the tank, and a recorder, which provides a record of the water level over a period of time. An instrument system may also have one or more alarms. Alarms are activated when the value of the process variable being monitored reaches a point that requires operator attention. In this instrument system, the alarms are activated when the water level in the tank is either too high or too low to ensure safe continuous operation. Alarms can be either visual or audible. Often, they're both. For example, this controller measures the signal it receives from the transmitter that represents the present value of the process variable and compares it to a preset value. This preset value is called set point. In this case, set point is the desired water level in the tank. If the signal matches the set point, the output from the controller does not change. However, if the signal is above or below the set point, the controller sends out a corrective signal. This signal goes to the final control element in the instrument system. In this case, the final control element is a level control valve that can be opened or closed by an actuator. This valve controls the water level in the tank by increasing or decreasing the flow of water into the tank. In this topic, we used a system that monitors and controls the water level in a tank to identify and describe the components of a basic instrument system. Now let's try some practice questions. An instrument system is a group of instruments and associated devices that work together to continually monitor a process variable. Some systems also control the value of the process variable. Alarms are activated when the value of the process variable being monitored reaches a point that requires operator attention. Since operators can't monitor all the different instruments associated with a process at the same time, most instrument systems contain alarms and other protective devices. Each alarm is designed to alert the operator when a process variable changes beyond an acceptable range. For example, the low-level alarm in this instrument system is activated when the water level in a tank falls below a predetermined minimum level. The high-level alarm is activated when the water level rises above a predetermined maximum level. Alarms can be visible, they can be audible, like this siren, or they can be both visible and audible. An alarm can respond indirectly to a condition if it's connected to the instrument system so that it monitors the signal from the transmitter, or directly if it's connected directly to the process being monitored. Alarms are usually activated by electrical switches, which are operated by sensing devices connected to the process. The sensing device can be mechanical, such as this pressure switch, which uses a Borden tube to respond directly to the pressure in a tank. Or the sensing device can be electrical, such as this thermocouple, which generates a voltage proportional to the temperature that it measures. In either case, when the value of the process variable reaches a specific point, The signal from the sensing device operates the switch, which activates the alarm. Each switch is able to operate in response to only one condition. For example, if the instrument system that monitors the water level in a tank has both a high-level alarm and a low-level alarm, each alarm has a separate switch. Each switch is set to operate when the water in the tank reaches a specific level. In addition to activating alarms, switches may also activate backup systems. For example, if this pump, which supplies water to a holding tank, fails, the water level drops to a point at which a switch activates the low-level alarm and activates a standby pump to help bring the water level in the tank back to set point. A switch may also be used as an interlock. An interlock ensures that a predetermined set of conditions exists before the status of equipment is changed to prevent equipment damage or harm to personnel. For example, this fan could be damaged if it's operated without proper lubrication. To prevent damage, an interlock pressure switch opens to shut off the fan's motor when the oil pressure in the motor is too low. The switch remains open to keep operators from turning on the fan by mistake until the oil pressure is high enough for normal operation. Controllers are devices that initiate action necessary to regulate the value of a process variable. In this water supply system, the controller receives a signal from the transmitter. The signal represents the level of water in the tank. The controller compares the transmitter's signal to the desired water level or set point. If there's a difference between the transmitter signal and set point, the controller sends a corrective signal to the final control element. In this case, the final control element is a flow control valve. Based on the corrective signal, the control valve opens or closes as necessary to regulate the flow of water into the tank and bring the water level back to set point. Controllers can be classified in several ways. For example, they can be classified by the process variable that they control, by whether they're electric or pneumatic, by functions they perform in addition to controlling the process variable, and by their location. The controller in this water supply system controls level. It operates by receiving a pneumatic signal from the transmitter, comparing that signal to set point, and sending a pneumatic signal to the final control element if necessary. So it can be referred to as a pneumatically operated level controller. Some controllers have a chart to record process variable values over a period of time. This controller could be called a recording controller. A controller can also be identified by its location. A controller that's located near the process it regulates is a local controller. Other controllers may be located some distance from the process, such as in a control room. These controllers are called remote controllers. Many controllers can operate in two different modes, automatic and manual. The controls and indicators used to switch from one mode to another are located on the controller. For example, this controller has a vertical scale with 2 pointers, a horizontal scale with a pointer, a set point adjustment knob, a thumb wheel used to adjust the final control element, and a selector switch used to change between automatic and manual control. Basically, the bottom portion of this controller is used during manual operation, and the top is used during automatic operation. In automatic control, or auto, an operator can adjust the set point by using the set point adjustment knob. The set point is indicated by one of the pointers on the controller's vertical scale. In automatic control, the controller compares the signal it receives from the transmitter to set point and generates an output signal that maintains the value of the process variable at set point. The value of the process variable is indicated by the second pointer on the vertical scale. When a system is not operating in a normal mode, an operator may need to take direct manual control of a process variable. In manual control, the operator sets the controller output signal directly by using the thumb wheel to adjust the position of the final control element as indicated on the horizontal scale. After the controller output is set, it will remain constant. This keeps the final control element in the same position until the setting is changed by the operator or until the controller is set to automatic operation. For example, this controller can be switched to manual operation at any time. However, for a smooth transfer back to auto from manual, the value of the process variable and the value of set point should be the same. Otherwise, rapid shifts in control action called bumps can occur. Bumps can adversely affect process operations, and they can sometimes damage equipment. To avoid bumps, the values of the process variable and set point should be equalized before a switch is made from manual to auto. A bumpless transfer can be done in one of two ways. In some cases, the value of set point is adjusted until it matches the value of the process variable. In other cases, the thumb wheel is used to adjust the position of the final control element until the value of the process variable is changed to match set point. Regardless of which method is used, once the two values match, the selector switch can be moved from one control mode to another without causing a bump. In this topic, we took a look at instrument system alarms and how switches may be used to activate alarms or backup systems or to act as interlocks. Finally, we saw how a controller can be identified, and we examined some of the steps necessary to switch a controller from one mode of operation to another. Now let's try some practice questions. Alarms can be visible, they can be audible, like this siren, or they can be both visible and audible. Alarms are usually activated by electrical switches, which are operated by sensing devices connected to the process. The controller sends a corrective signal to the final control element. In this case, the final control element is a flow control valve. This controller can be switched to manual operation at any time. However, for a smooth transfer back to auto from manual, the value of the process variable and the value of set point should be the same. Otherwise, rapid shifts in control action called bumps can occur. Bumps can adversely affect process operations, and they can sometimes damage equipment. To avoid bumps, the values of the process variable and set point should be equalized before a switch is made from manual to auto. Valves regulate the flow of gases and liquids in process systems. A valve that is operated automatically to throttle flow is usually referred to as a control valve. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve where the disc rotates to open and close the valve. This is a typical control valve. The valve body contains the disc and the seat. The valve stem is attached to the disc so that the disc can be moved up and down to open and close the valve. The upper end of the valve stem is connected to an actuator. The actuator provides the power to move the valve stem in response to signals from the controller. Many different actuators can be used with control valves. Three general types are pneumatic, hydraulic, and electrical. The actuator on this control valve is a pneumatically operated diaphragm actuator. This type of actuator is commonly used in many process systems. An actuator is commonly operated by a corrective signal from a controller. However, in some cases, as in this pneumatic diaphragm actuator, the air pressure from the controller's signal alone is not enough to operate the actuator. To overcome the forces of friction in the actuator and the valve stem, and the fluid pressure against the valve disc, an actuator can be operated by a separate supply of higher pressure air. The higher air pressure is regulated by a valve positioner. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. When the process variable in this system needs to be adjusted, the controller sends a pneumatic signal to the positioner. Then the positioner regulates the separate supply of higher pressure air to the actuator to move the valve to a new position. As the valve stem moves up or down, it moves the linkage. When the linkage indicates to the positioner that the valve is in the position called for by the controller, the actuator movement is stopped. In addition to valves, there are many other types of final control elements. Two of the most common are dampers and motors. Dampers, which are often called louvers, use a number of adjustable parallel vanes or blades to control the flow of air and other gases. In some systems, dampers have a pneumatic actuator with a positioner that controls the position of the vanes. During operation, when the positioner receives a signal from a controller, it supplies air pressure to the damper actuator. The actuator then opens or closes the vanes to position them according to the signal from the controller. Motors are also used in some process systems as final control elements. Motors provide the driving force to move, operate, or position components. For example, this variable speed motor is used to run a conveyor. Changing the electrical power supplied to the motor changes its speed, which slows down or speeds up the conveyor. While some motors are variable speed motors, many of the motors in a plant operate at only one speed. The output speed from a single speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element. For example, this fan supplies air to a process system. It's connected to a motor through a coupling that can regulate the speed at which the fan blades rotate. When the supply of air from the fan needs to be changed, a signal is sent from the controller to an actuator connected to the coupling. The actuator adjusts the coupling to alter the speed of the fan, which changes the amount of air supplied to the system. In this topic, we saw how a control valve can be used as a final control element. We also looked at how pneumatic actuators and positioners are used to position valves. Then we examined some other components that can be used as final control elements. Now let's try some practice questions. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve, where the disc rotates to open and close the valve. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. The output speed from a single-speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element.